The formation of the solar system and Earth, circa 4.6 to 4.0 billion years ago. Section 1. Before Earth, a cloud of star remains, before Earth had oceans, before the moon crossed the night sky, before mountains, continents, weather, life, or a single living cell. There was a cloud, a vast cold region of gas and dust drifting through the Milky Way. This cloud was not empty. It carried the remains of older stars, hydrogen from the early universe, helium from the beginning of cosmic time, carbon, oxygen, silicon, iron, magnesium, sulfur, and other heavy elements forged in stars and scattered by supernovae. The raw material of worlds was already there, but it had not yet become a world. Section 2. The solar system begins. Then gravity began to gather it. A dense region within the molecular cloud started to collapse. Slowly at first, then with growing force, material fell inward. As the cloud contracted, it began to spin faster. The same motion that makes a skater spin faster when pulling their arms inward shaped the collapsing cloud into a rotating disk. At the center, most of the mass gathered into a young star, the Sun. Around it, the remaining gas and dust flattened into a wide spinning disk, a protoplanetary disk. This was the birthplace of the solar system, not a completed system, not finished planets neatly placed in orbit, but a storm of dust, gas, ice, rock, metal, heat, gravity, and collision. Everything was moving. Everything was interacting. Everything was becoming. Section 3. The first solids. The oldest preserved solids from this ancient time are tiny minerals found inside primitive meteorites. They are called calcium-aluminum-rich inclusions, or CaIs. These objects formed about 4.567 billion years ago, and scientists use them as the starting clock for the solar system. This was not the moment every planet appeared. It was the first preserved evidence that solid material had begun forming around the newborn sun. From there, the disk became a cosmic construction zone. Microscopic dust grains collided. Some bounced apart, some shattered, some stuck together. Dust became aggregates, aggregates became pebbles. Pebbles concentrated into larger bodies. Through gas drag, turbulence, gravity, and collisions, the smallest solids began building the first planetesimals. Planetesimals were the seeds of planets. Section 4. Dust becomes worlds. Some planetesimals were only kilometers wide. Some grew larger. As their mass increased, their gravity strengthened. They pulled in more material. They collided with other bodies. They merged, broke apart, and merged again. Over time, the inner solar system filled with planetary embryos, bodies as large as the Moon or Mars, moving through unstable orbits around the young sun. This was not a peaceful birth. It was a violent one. The planets were built by impact. Section 5. The first ideas about planetary formation. Long before spacecraft or telescopes, thinkers tried to understand this mystery. In 1755, Immanuel Kant proposed that stars and planets could form naturally from rotating clouds of matter. He imagined a universe where cosmic systems emerged through physical processes rather than remaining fixed and eternal. In 1796, Pierre-Simon Laplace developed a related nebula model. His details were not fully correct by modern standards, but the central idea survived. The Sun and planets formed from a rotating nebula. Kant and Laplace did not have meteorite dating. They did not have computer simulations. They did not have spacecraft, lunar samples, or modern physics. But they helped point humanity toward one of the most important truths in planetary science. Worlds have histories. Planets are not placed fully formed into space. They are built. Section 6. Planetary formation becomes a science. Much later, Scientists such as Viktor Safronov and George Wetherill turned planetary formation into a quantitative science. They studied how small bodies grew, how planetesimals collided, how planetary embryos accumulated mass, how rocky planets like Earth could emerge from a disk of debris. The modern picture became clearer. The solar system was not born finished. It assembled through gravity, impact, motion, and time. And in the inner solar system, one growing body would become Earth. Section 7. Earth begins to form. The young Earth did not appear all at once. It grew through accretion. Rocky and metallic bodies repeatedly collided and merged. Each impact added mass. Each collision changed the young planet. Some impacts shattered material. Others joined bodies together. Over millions of years, the proto-Earth became larger, hotter, and more gravitationally powerful. Earth did not suddenly develop gravity. Every grain of dust already had gravity. Every rock already pulled on every other rock. But as Earth's mass increased, its gravitational attraction became stronger. It could pull in more material. It could hold itself together more powerfully. It could capture, collide with, and absorb larger objects. The young Earth became a growing world of heat and violence. Section 8. A planet melts and separates. Several forces heated the young Earth from within. Impact energy became heat as bodies slammed together. Gravitational compression warmed the interior as the planet grew. Radioactive isotopes released energy as they decayed. And as dense metals sank inward, the movement of material released even more heat. Large parts of the young Earth melted. This allowed the planet to differentiate. Heavy iron and nickel sank toward the center. Lighter silicate rock rose above them. The core began to form. The mantle took shape. The outer layers cooled and began producing early crust. Earth was becoming internally organized. A planet with layers. A metallic heart. A rocky mantle. A surface that would one day hold oceans. Section 9. The violent young Earth. The early Earth was still far from the world we know. Its surface was unstable, its atmosphere was harsh, its crust was young and fragile. Impacts continued. Volcanism reshaped the surface. Molten rock rose and cooled. The planet was being built and destroyed at the same time. Earth's age is about 4.54 billion years, but that age was not discovered by looking at an untouched piece of original Earth. Earth's earliest rocks were mostly destroyed, recycled, melted, buried, or transformed by geologic activity. To find Earth's age, scientists had to look outward. Meteorites preserved the early history of the solar system better than Earth's surface did. In 1956, Claire Patterson used lead isotope measurements from meteorites to establish the age of Earth with remarkable accuracy. The rocks of Earth had changed, but the meteorites remembered, and through them, humanity learned the age of its planet. Section 10. The Giant Impact. Around 4.5 billion years ago, near the end of Earth's main growth, another world entered the story. A planetary embryo, large, fast, dangerous, often called Theia. Theia was probably about the size of Mars, though the exact size and impact conditions remain debated. It struck the proto-Earth. The collision was enormous. A world hit a world. Rock, metal, and vapor blasted into space. The young Earth was reshaped. Material from the impact spread into orbit around the planet. Some of that material formed a hot debris disk. From that disk, gravity gathered fragments together. The moon began to form. Section 11. The birth of the moon. The moon was not simply captured fully formed from space. It was probably born from Earth's greatest collision. A child of impact, a companion made from the wreckage of a planetary disaster. Evidence from lunar samples, meteorites, and simulations supports this giant impact hypothesis. The Moon's small metallic core, its relationship to Earth's chemistry, and the angular momentum of the Earth-Moon system all point toward a violent origin, but the exact details remain one of the great puzzles of planetary science. How large was Theia? How fast did it strike? At what angle? How much of the Moon came from Earth? How much came from the impactor? How did the Earth and Moon become so chemically similar? The answer is still being refined. Science does not freeze at the first explanation. It tests, revises, and rebuilds. But the central picture remains powerful. The Moon was likely born from one of the most violent events in Earth's history. Section 12. The Moon's influence on Earth. After that violence, the Moon became one of Earth's most important companions. The Moon shaped tides. Its gravity pulled on Earth's oceans. It affected Earth's rotation. Through tidal friction, Earth's spin gradually slowed and the Moon slowly moved farther away. The Moon also influenced Earth's axial behavior, helping moderate some variations in the planet's tilt over long periods of time. It did not guarantee a perfect climate. It did not make life inevitable. But it became part of Earth's physical evolution. The Earth and Moon became a system, a planet and its companion, a world and the scar of its own creation. Section 13. Earth begins to cool. After the moon-forming impact, Earth was still young, still hot, still unstable, but it began to cool. For a long time, people imagined the Hadean Earth as a completely molten hellscape, a planet of endless magma, fire, and bombardment, and parts of that image are true. The young Earth experienced magma oceans. It suffered major impacts. Its surface was repeatedly melted, buried, and transformed. But the full story is more complicated. Some parts of Earth cooled surprisingly early. The evidence comes from tiny minerals called zircons. Section 14. Ancient zircons and early water zircons are small, durable crystals. They can survive events that destroy the rocks around them. Some of the oldest zircons come from the Jack Hills region of Western Australia. One zircon grain has been dated to about 4.404 billion years old. That tiny crystal tells a huge story. It shows that solid crust existed very early in Earth's history, and some ancient zircons carry oxygen isotope evidence suggesting that their source rocks interacted with liquid water. This means that by roughly 4.4 to 4.3 billion years ago, parts of Earth may have cooled enough for crust and liquid water to exist. Not necessarily oceans like today, not necessarily continents like today, not necessarily a stable blue planet, but crust, water-rock interaction, cooling, possibility. The early Earth was not simply a ball of lava for hundreds of millions of years. It may have moved between destruction and recovery, impact and cooling, melting and crust formation, violence and water. This is where Earth begins to become more than a planet. It begins to become a place. Section 15. The Age of Impacts. The solar system was still dangerous. The early inner solar system was filled with leftover debris, asteroids, planetesimals, fragments from planetary formation, bodies whose orbits were unstable. Some were thrown into the sun, some were ejected into space, some struck planets and moons. Earth and the Moon were repeatedly hit by incoming objects. On Earth, much of that ancient impact record has been erased by erosion, volcanism, and tectonic recycling, but the Moon preserves scars better. Without plate tectonics and without strong erosion, the lunar surface became a record of ancient bombardment. Section 16. The Late Heavy Bombardment. Debate for decades, scientists studied lunar rocks brought back by the Apollo missions. Some appeared to cluster around ages near 3.9 billion years ago. This led to the idea of a late heavy bombardment. A sudden spike of impacts in the inner solar system, a lunar cataclysm, a time when asteroids and comets may have battered the young worlds with renewed violence. But the story is not settled. Apollo samples came from limited regions. Some rocks may have been affected by debris from the massive Imbrium impact. Impacts can reset radiometric clocks. Age clusters may reflect sampling bias instead of a true solar system-wide spike. Today, the strongest statement is more careful. Early impacts were intense. Earth and the Moon were struck often, but whether there was a sudden, short, late, heavy bombardment around 3.9 billion years ago remains debated. The bombardment may have declined gradually, or it may have included a spike. The evidence is still being tested. Section 17. Impacts destroy and deliver. Whatever the exact pattern, impacts mattered. They were destructive. They could melt crust. They could vaporize water. They could destroy organic molecules. Large enough impacts could temporarily sterilize surface environments. But impacts could also create. They could deliver water-bearing minerals. They could bring carbon-rich material. They could carry organic compounds. They could excavate fresh mineral surfaces. They could generate hydrothermal systems where heat, water, and rock interacted. Destruction and delivery came together. The same falling bodies that threatened early Earth may also have helped supply the ingredients for future chemistry. Section 18. Water and organic material. Carbon-rich asteroids and primitive meteorites contain water-bearing minerals and organic compounds. Some contain amino acid precursors and nucleobases, chemical building blocks related to life. Samples from asteroids such as Ryugu have strengthened the evidence that complex organic chemistry occurred inside primitive solar system bodies. This does not mean asteroids brought life to Earth. It means they may have brought ingredients, water, carbon, nitrogen, organic molecules, materials that early Earth could use. Comets may also have contributed, but Earth's oceans were probably not delivered by comets alone. Some water was likely built into the material that formed Earth. More may have arrived later from asteroid-like bodies and possibly comets. Earth was not assembled dry and then filled from one source. It was shaped by many sources: original accreting material, volcanic outgassing, asteroids, possibly comets, impacts, cooling, chemistry. Section 19. Earth becomes potentially habitable. By around 4.0 to 3.8 billion years ago, Earth may have possessed several environments where prebiotic chemistry could occur. Habitability does not mean life. A planet can have ingredients without biology. A world can have water without cells. A chemical environment can be promising without being alive. But the conditions were becoming more interesting. Earth had liquid water. It had volcanic activity. It had hydrothermal systems. It had carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur-bearing compounds. It had metal-rich minerals. It had clay-rich surfaces. It had chemical gradients. It had heat. It had ultraviolet radiation. It had lightning. It had geothermal energy. It had places where molecules could form, concentrate, react, and transform. Section 20. Possible birthplaces of life. Several possible birthplaces of life have been proposed. Deep-sea alkaline hydrothermal vents may have provided natural mineral compartments and chemical gradients between hydrogen and carbon dioxide. Volcanic hot springs and ponds may have allowed wet-dry cycles, concentrating molecules and helping them link into longer chains. Mineral and clay surfaces may have helped organize and catalyze chemical reactions. Impact-generated systems may have created temporary hydrothermal circulation and fresh reactive minerals. Ice and cold environments may have concentrated molecules between crystals and protected them from some destructive processes. Each environment has strengths, each has problems. No one has yet proven where life began. Hydrothermal vents offer continuous energy but may dilute fragile molecules in the ocean. Surface ponds can concentrate chemistry but require stable exposed land. Minerals can catalyze reactions but do not automatically create self-replicating systems. Impacts can provide energy and ingredients but can also destroy complexity. Ice can protect chemistry, but its role on early Earth remains uncertain. This is the frontier between geology and biology, between chemistry and life, between a planet that is merely habitable and a planet that is alive. Section 21, Before Life. Some evidence has been proposed for life around 3.8 to 3.7 billion years ago, including carbon isotope patterns, possible microbial structures, and mineralized filaments. But that evidence remains difficult to interpret. Geology can imitate biology. Non-living processes can sometimes produce patterns that look biological. The stronger and more abundant evidence for life appears later, around 3.5 billion years ago. So in this age, we should not say life had definitely appeared. We should say Earth was becoming capable of supporting the chemistry that could lead to life. The stage was being prepared. The planet was cooling. Water was present. Crust existed. Impacts continued. Volcanoes released gases. Minerals reacted with water. Energy flowed through environments. And somewhere in this restless young world, the ingredients of life were beginning to gather. Section 22. The early atmosphere. Earth's atmosphere was nothing like the air we breathe today. There was almost no free oxygen, no oxygen-rich blue sky, no ozone layer protecting the surface the way it does now. The atmosphere was shaped by volcanic gases, water vapor, carbon dioxide, nitrogen, and other compounds. If life existed then, it would have been anaerobic. It would not have breathed oxygen. The oxygen-rich atmosphere would come much later, after life itself changed the planet. But at this point, Earth was still prebiotic or barely approaching biology. It was a world of chemistry, a planet between fire and life. Section 23, the age of planetary formation. From 4.6 to 4.0 billion years ago, the story of Earth was not a simple march from dust to a finished planet. It was overlapping chaos. A molecular cloud collapsed. The sun ignited. A disk formed. Dust became planetesimals. Planetesimals became embryos. Embryos collided. Earth grew. Earth melted. Iron sank. The core formed. The mantle separated. The crust began. A giant impact created the moon. Water interacted with early rocks. Impacts battered the surface. Volatiles and organic compounds were delivered and redistributed. Hydrothermal systems and volcanic environments emerged. The ingredients for life began to assemble. This was the age of planetary formation, the age when the solar system became real, the age when Earth was hammered, melted, divided, cooled, and transformed, the age when a violent young planet became a possible home. Section 24. Earth enters the timeline. Nothing about this process was gentle. Earth was born from collision. Its moon was born from catastrophe. Its surface was reshaped by impacts. Its chemistry was supplied by dead stars, meteorites, volcanoes, water, heat, and time. And yet from that violence came potential. A planet with a core, a planet with a mantle, a planet with crust, a planet with water, a planet with chemistry, a planet that could one day become alive. Before life could begin, Earth had to be built. Before oceans could cradle biology, the planet had to survive fire. Before cells, there had to be chemistry. Before chemistry, there had to be elements. Before elements, there had to be stars. And before humanity could ever look up and ask where it came from, the solar system had to form from the ashes of older suns. This is where Earth enters the timeline, not as the world we know, not yet blue, not yet living, not yet calm, but forming, burning, cooling, changing, a young planet in a violent solar system, a world made from dust, impact, gravity, metal, rock, water, and time. And hidden within that chaos was the first possibility of everything that would come next.